Ladies and gentlemen, welcome to AFOMP webinar. I think this is our fourth webinar, 4 months webinar. Actually, we have another is called score webinar, which takes a little longer for 3 hours. And today, we are lucky to have Dr. Fukuda and Dr. Yang to organize this webinar. Firstly, I would like to give a brief introduction of our moderator, Dr. Bing Yang. Also, he called him Kimi Bing Yang. Dr. Yang obtained his bachelor degree in science with honor of excellent graduate from Nanjing University in 2007 in China. In 2011, he graduated from the University of Hong Kong with a doctorate degree. He was granted the professional qualification of certificate medical physics by Hong Kong Institute of Physicists in medicine with demonstrated working experience and qualification in radiotherapy. He is currently working as an acting assistant senior medical physicist in Hong Kong Sanatorium Hospital. He has been serving as the secretary of Hong Kong Institution of Physicists in Medicine and as education and training committee member of AFOMP. Since 2018, he has published more than 30 research works in international journals and given more than 50 oral poster presentations at the international conference. His research interests are mainly in motion checking techniques, MR-guided research, and proton therapy. Please, Dr. Yang, I will give you the microphone to you. Thank you.
Okay, thank you. So, could you hear me?
Yes.
Yes.
Okay. So hi everyone, a warm welcome to the online webinar on the introduction to radiation oncology project of FNCA. So I'm your moderator for today's session. So my name is Kimi. So I'm thrilled to guide you through this informative event. Before we begin, I would like to express our gratitude to Professor Fukuda for sharing his expertise with us. Professor Fukuda is a renowned authority in the field of radiation oncology and has played an important role in advancing research and development efforts in the Forum for Nuclear Cooperation in Asia. So Professor Fukuda obtained the PhD in 1994 at Osaka University and currently serving as section manager of radiation quality control section at QST Hospital. Professor Fukuda has been actively involved in various research projects and has published extensively on this subject. He's active in playing important roles in various international institutions and organizations, such as IOMP, AFOMP, GSMP, and JBMP. So Professor Fukuda's academic achievements are also remarkable. He served as an editor and reviewed for international journals and was invited to be chaired for many international conferences. And he has over 90 publications. So for today's webinar, we encourage active participation from all the attendees during the webinar. If you have any questions for Professor Fukuda, please use the chat function and to leave your questions, and we will have a dedicated Q&A session at the end. So now please join me in giving a warm virtual welcome to Professor Fukuda. So Professor Fukuda, the stage is yours. Let me start sharing screen.
Okay, thank you. Can you see my presentation?
Yes, yes. Very
Thank you.
clearly.
Thank you. Yes, thank you. Kimi-san, nice introduction. So I'm Shikegazu Fukuda. Usually, so I work for the carbon therapy as a medical physicist. But today, so I want to talk about the international collaboration, radiation oncology project of FNCA. So content is here. What is FNCA for nuclear cooperation in Asia? And I explained the radiation oncology project of FNCA. And I want to talk about the documentary audit for radiation oncology project of FNCA. What is FNCA? So FNCA is a framework for international cooperation for the peaceful use of atomic energy led by the Cabinet Office and Ministry of Education, Culture, Sports, Science, and Technology of Japan. So 12 countries, so also India, Bangladesh, China, Indonesia, Japan, Kazakhstan, Korea, Malaysia, Mongolia, Philippines, Thailand, Vietnam, conducting collaborative activities under the core partnership for joint research on nuclear science and technology, information exchange, and support for nuclear power infrastructure development. For FNC meeting consists of the two meetings. One is the FNC ministerial level meeting. So this meeting of ministerial level representatives who are in charge of science and technology policy and supervising nuclear energy and radiation usage, FNC's cooperation policies and nuclear energy policies of the member countries discussed in this meeting. So senior officials from member countries have preliminary discussion on agenda for the ministerial level meeting. This picture shows the FNC meeting held in Ulaanbaatar last year. And the coordinator meeting, a coordinator is appointed for each member country to oversee FNC project activities in various nuclear fields. Coordinators gather to assess the progress of individual projects and discuss their results, evaluation, future policy, and general management of FNCA. This shows a list of the national coordinator of each country. You can see coordinator of your country. For study panel, in the study panel, senior official and expert from the FNC member countries discuss on nuclear policy technical matters of both power and non-power areas of nuclear energy with a view to applying such knowledge to domestic and international activities. And the energy project, so we have the 7 projects in 4 areas associated with the radiation utilization and the nuclear power infraction, nuclear safety strengths, and nuclear infraction strengths. And radiation utilization and development field has 2 subfields: industrial environment utilization and healthcare utilization. So in industrial environment utilization, the 4 projects: mutation, breeding using radiation processing and polymer modification, and combating food fraud project. So radiation oncology project belong to the healthcare utilization subfield. Next is the radiation oncology project of FNCA. So this the purpose of this project, radiation oncology project, is to establish optimal treatment protocol of radiotherapy and chemotherapy for predominant cancer in Asia. And second is to improve the quality of radiotherapy in FNCA member countries, and to improve treatment outcomes of predominant cancer in Asia. So 11 countries joined this project. So concrete project activities like this, one is the international multi-center clinical studies to make a common protocol for the radiotherapy and physical QA/QC of radiotherapy. And in the workshop, so we perform the education activity, for example, open lectures, hands-on training. And additionally, so we are trying to make a collaboration with IAEA, RCA project. So international multi-center clinical studies. So this shows the timetable of the clinical studies. So we started making a protocol since 2000, especially the cervical cancer and NPC, and since 2014, so we started breast cancer. Today, so I want to focus on the cervical cancer and new latest protocol. We call it the cervix 5. So cervical cancer is the first most common cancer in women and the seventh overall, with an estimated 500,000 new cases and 260,000 deaths in 2012, predominantly in low or middle income countries. This shows the cervix 5 protocol. So the protocol period, the period of treatment, 8 weeks, and combination of EBRT and 3D-IGLT chemotherapy. We perform EBRT 6 weeks and a half. And each week we apply the chemotherapy like this. And after 4 weeks, so we perform the 3D IGBT to deliver the higher local dose to tumor like this. So this shows the planning of 3D IGRT. And 3D IGRT is a cutting-edge radiotherapy for cervical cancer, which enables optimal dose delivered to the tumor with minimized doses to OARs. So 3D IGRT may improve local tumor control and decrease incidence of radiation toxicity. This shows the clinical result just only the 2 years, but very good outcome. We got a very good outcome, clinical outcome. So FNCA 5 study have yielded several treatment outcomes with low rate. So of course, we will check the outcome status at least 5 years. Next is the physical QA/QC of radiotherapy. So we performed the dosimetry audit for radiation oncology project of FNCA. So as you know, so physical QA/QC of radiotherapy is essential for accurate radiotherapy. So FNCA medical physicist team carried out dosimetry audits or EBRT and brachytherapy in institutions of FNCA member countries. So for the external beam radiotherapy, as a postal audit or on-site audit, so we perform the intercomparison of the reference dose using radio photoluminescence glass dosimeter, RDD. And in the case of site audits, we additionally perform the external dosimetry audit using the ionizing chamber. And for brachytherapy, we perform only the on-site audit now, one is to check the source strength check with well-type chamber, applicate offset check, and source step accuracy with using radiochromic film. And as a feasibility study, so we performed the end-to-end test for 3D IGBT. As you know, from the CT taking, therapy planning, and those comparison using IC and RGT. I talked about the intercomparison of the reference source using RGB. So radiophotoluminescent glass dosimeter RGB is a silver activated phosphate glass, and density is 2.61 gram per cubic per centimeter. This means that RGD is not water equivalent, and the size is 1.3 meter in diameter, and the length is 12 millimeter. So glass dosimeter principle is this. So radiation produces RPL centers, which emit orange luminescence by UV ray excitation. After emitting luminescence, they will return to the stable RPL center. Therefore, the numbers of RPL centers stay constant. So this allows infinite or repeatable infinite numbers of reading of the same irradiation. So usually, so output of glass dosimeter average of 5 times sequential reading. And RPL centers can be cleared by annealing. For example, so 400 degrees with 13 minutes. So we can use the element of sequentially and repeatedly. This shows a schematic picture of the reader, and the 20 glass dosimeter elements are set in this magazine and read on the same time. So N2 laser come from this direction to the glass dosimeter, and we can read using a multiplier. This shows those reading system, reader and controller and annealing oven. So these are result of this shows the elemental dependence on for the dependence of element of glass dosimeter. From these results, we can decide the calibration factor of each element. Besides, we perform same measurement for the other energy, and this is the result for the 4MB, 6MB, 10MB X-ray. So dependence are almost the same. So factor for the energy difference with plus minus 1%. So we decided no significant energy dependence around the high energy 4MB and 10MB. We use tap water phantom. So tap water phantom is a water equivalent solid phantom, and the density is almost the same that of water. And mean atomic number is also same to the water, and the electron density is also near to the water value. Size is 30 centimeter and 30 centimeter, and there are some some hold. So we can set the RGD RGD parts on into this solid phantom. And usually, so we some solid this RGD contains tap water phantom over the solid phantom, or to consider about the backscatter effect, and align the ice center by using the crosswire and laser. And we pile up tap water 2 centimeter depths. And usually we irradiate the X-ray 1 gray to 2 set blast dosimeter for each energy. This picture the RGD dosimeter audit performed at NCCM and Ulaanbaatar. So this is the schedule of the audit, EGRT audit. Since 2006, from China, Korea, Indonesia, Vietnam, Philippines, Japan, Malaysia, Thailand, Bangladesh, Pakistan, Vietnam, Pakistan, and Thailand. Until this, so we performed 46 beams from 11 countries until the 2014, and we published the result of audit as this paper. And last year, we performed this audit in Mongolia, National Cancer Center of Mongolia, NCCA, because they installed the LINAC, I think in the 2019 or 18 as the first one of Mongolia. So this shows the result of the audit using RGD. So majority of the beam energy between 6 and 50 MV, and the deviation with 1% of this energy or other energies. So deviation was around slightly higher than 1%. But these are limited statistics because the number of the 4 MV and 80 MV beams test was only 1 and 3, respectively. The average and the standard deviation of the relative deviation between the measured and described dose among 46 beam was 1.5%, and the deviation is standard deviation is 1.5%, respectively. So taking into account the uncertainty values of RGB of 1.1%, the deviation is excellent from the point of view of the uniformity of the multi-country data. So right figure shows the histogram of relative deviation. More than 90% of the beam were within the plus minus 3%. Only one beam exceeded the tolerance level of plus minus 5%. So for these irregular values, so we investigate the cause and concluded that the operator miswrote, miswriting the pressure value as 106 instead of the true value 100.6 in the Excel-based database. This difference corresponds to a 5% underestimate of correct factor of temperature and pressure that leads to an overdose of exactly the same percentage, near 60%. So as a result, so 6.1% overdose measured by our dose audit could be attributed to this mistype. So the information was immediately sent as feedback to the hospital, together with a message stating the importance of accurate typing and double checking of parameters. Next is for the audit, practice of the audit. So to check the source strength check and the fricate offset check and the source step accuracy. So dosimetry audit for the brachytherapy, its purpose is to improve the quality of clinical study among cooperative facilities, especially so as mentioned, so subjects 5 protocol. And additionally, so as a feasibility study, so end-to-end test the dosimetry audit have been conducted for 3D image guided brachytherapy. We started this on-site audit since 2019. Japan, Korea, China, Philippines, especially so in 2020, we made the audit for the 3 beams. Yes, last year we performed this audit in FNCA in Mongolia. This shows the modalities for each institute. Almost they use Iridium 192, all activity almost same, and GPS on central or Eclipse, and image acquisition they use CPU. But so slice thickness has some variety from 1 millimeter to 3 millimeter. FOV almost same. So since 2020, so we extended this methodology for the cobalt 60 modality. So like this, I don't know if that details of this GPS or some plan. So for the strength check, we use a well type chamber for the source strength measurement and the consideration of several corrections. And this shows some results of the source strengths. And well type IMD chamber, we use HDR 1000 plus, which that was calibrated our standard dosimetry laboratory in Japan. 2020 was used. And for the cobalt 60 source holder, we use reference 70,110. So for the cobalt source, we need additional correction factor, which is derived with the baby cobalt source was applied 1.05. So this value was obtained from this paper. So yes, major difference is between the measurement and the TPS is less than with the 3%. So tolerance within the tolerance and very good result. And we use EBT film to check the applicator offset like this. So as you know, so applicator offset is one of the critical parameters of image-guided brachytherapy. And the distance from outside tip of applicator to center blade to active source derivative distal position. And additionally, so we check the source step accuracy of the checking using the radiographic film of tandem applicator. We ordered the operator to deliver 1 centimeter steps, for example, to 12 seconds, one each position. And we check the accuracy is less than 1 millimeter using the ruler. Of course, precise analysis was done using film scanner system, and we got a very good result. That means the discrepancy is less than 1 millimeter. This shows the applicator offset to institution. This is an example of the result. Difference is less than 1 millimeter. And finally, I want to explain the end-to-end test for 3D IGBT and the feasibility studies. So we use an end-to-end test using ion chamber, especially pinpoint chamber for the immediate dosimetry at the A points. And we all performed also RGD using RGD evaluated prescribed dose at A points and so OAR. So now we are the reason we use RGD is we want to develop the postal audit or postal and remote audit in future. So this is the workflow of using ion chamber and RGD. So firstly, so we prepare the dosimeter, calibration of dosimeter. And next is the setup quantum and applicator, and taking the CT imaging and perform the treatment planning and irradiated the prescribed dose to the pinpoint chamber or RGD. So these parts conducted in the visited hospital. And for the RGD, we read the RGD signals in our institute QST. So preparation for the dosimeter, so response calibration was done using our cobalt 60 source. And setting of phantom applicator, we developed the phantom like this, and we can set the applicator near like a clinical situation like this. And take a CT image. When we take a CT imaging using a dummy dosimeter, the dummy dosimeter have a sphere cavity 2 millimeter diameter corresponds to the reading area of RGD. So you can see the position of the dosimeter. And we ask the operator or medical physicist in that visited hospital make a treatment planning. And for example, I ask prescribed dose is 6 gray in each A point. And so we irradiate those to pinpoint a chamber or RGD. So when using RGD, so each RGD is inserted their dosimeter holder and located Manchester point A, right and left, or reference point for evaluating bladder or rectum dose are recommended by ICRU. And when we use ion chamber, pinpoint chamber, only we can measure the point A, R and L. And so after irradiation, so we read those signals from RGD in our institute. This shows an example of reports, and the final result is here. This shows the difference measured value in TPS after the A point. And another, this value is difference between the measured value and the TPS at the OAR, bladder, and rectum. So you can see the large difference using RGD method. So this shows the other result, TPS percentage shows the ratio of difference measured in TPS. And the point A and rectum dose are consistent with 5%, but not for the bladder dose. So the partial reason is we use only the linearity correction factor was applied to the RGD data. So furthermore, it is necessary to apply the energy correction factor. So now we're estimation radiation quality using the Monte Carlo simulation to get more precision results. So we are writing a paper describing the result of the feasibility study of this end-to-end test for IGBT in detail. Okay, so this shows the educational activities, open lecture, and training. So open lecture includes, of course, IGBT and cutting-edge radiotherapy, for example, carbon therapy or proton therapy. And we perform the hands-on training on the 3D IGBT. And finally, we are trying to make a collaboration with IAERC, RCA. So as you know, so medical physics region, so IAERCA performs these projects. For example, last 638 medical physics through education and training. And this project will lead to next project, and latest project is last 6101, improving the quality and safety of radiation medicine through medical physics education training, RCA. So FNCA is a framework for international cooperation for the peaceful use of atomic energy. And the radiation oncology project is one of the 7 LNC projects, and the purpose is establishing a treatment protocol of radiotherapy, chemotherapy for predominant cancer in Asia, and to improve the quality of radiotherapy in FNCA member countries, and to improve treatment outcomes of predominant cancer in Asia. And the FNCA medical physicists team carried out dosimeter audit for EBRT and brachytherapy in institution of the FNCA member countries, and feasibility studies of end-to-end tests for IGBT has been continued to make it a common audit method. Acknowledgement, we want to thank you for the Japan National Coordinator, Mr. Wada. And of course, medical physics team, especially Dr. Mizuno, so he developed the RGD audit, and IAEA adapted his method, and other medical physicist members. Of course, medical doctors teams, and he is a project leader, so Dr. Kato. Okay, so thank you very much. Thank you for your attention.
Thank you, Professor Fukuda, for bringing a wealth of experience and expertise to this webinar. So let me see if there's any question here. Yeah, there's one question from Molina. So, sir, is the multi-centric hospital project, is the studies related to some specific centers or all cancer patients?
I think this question is multi-hospital project is a study related to some specific cancer. Yes, especially to predominant in Asia. So we selected cervical cancer and NPC and breast cancer, and to all cancer patients. Yes, we want to say we want to spread this common protocol to all Asia countries. So the point is how to say, so all hospitals can perform this protocol treatment of this protocol. Yeah.
Okay. Oh, I also have some questions for Professor. So it's good to know that the FNCA provides the service of those audits. So I would like to know, is it free of charge, or if no, so is it expensive?
So in future, so we want to perform the all audit as a postal audit or a remote audit. In that case, the expense or charge will be how to say cheaper than this. And so in the FNCA project, this activity is almost the volunteer. So there is no charge.
Oh,
there are no charge. Yes.
So I saw another question is coming. So how can we participate in the dosimetry audit for brachytherapy?
Yes. Please contact me, or please contact your national coordinator, or yes. So if you don't know the national coordinator, please contact me. So
that's good.
We transfer.
Thank you, Professor.
Yeah, you are interested to your country's coordinator.
Okay. I also noticed that for the those audits, yeah, so you only perform measurement for the flattened beam, right? So do you have any plan for like a flattened filter beam, or do you have any plan for like particle therapy dosimetry in the future?
Yeah. Nowadays, so there are many proton centers in Asia.
Yeah.
So yeah, in future, so we should make some international comparison of the dose and etc. And but so FNCA is appropriate for the dose comparison or not. I don't know. But so for proton therapy, so we made as you know, so PTCOG AO, PTCOG Asia Oceania group. So and we are start to make some medical physicist groups related to the PTCOG AO. So in that group, so we are planning to make some international comparison among the proton centers.
Oh,
yeah.
Thank you. Thank you for the effort. Well, I'm looking forward to the results from you.
Yeah.
and also that I think from my understanding, the current commercial TPS like Alcentra still use the TG43 data, right? So do you think like Monte Carlo based TPS will help for the brachytherapy, or is it Monte Carlo important for brachytherapy?
So as you know, so the TPS for the brachytherapy handles how to say, so body as a water equivalent.
Yeah.
Yeah, so that there is some reason, of course, brachytherapy. So I think yes, for the brachytherapy, so water equivalent handling is enough in this situation. Of course, so in future, so Monte Carlo simulation will be helpful for the more precise treatment. But not now, I think.
Indeed. Yes, I also do agree with you about the like the trending or the future of the 3D the RGBT.
Yes.
But this is a cutting edge technique. So in our hospital, we actually use the MR guided brachytherapy.
Brachytherapy.
Yeah.
Okay.
So, yes, but as we all know, the 3D IGBT is kind of labor intensive and time consuming. So not all oncologists love this. So actually, hospital maybe like less than 50%. So I would like to ask, maybe in your hospital, QSC hospital, is the 3D IGRT popular in your city? In your hospital?
Yes. And in Japan, so there are many hospitals performing 3D IGRT with CT and or sometimes using the MRI. Yeah.
Oh, okay, that's good. Yeah, really, Japanese people are lucky, I think.
Oh, there another question. So if overseas facility were to perform the postal audit, which they said only RGDs from Japan. No, so we want to send RGD and our Phantom for the 3D RGRT audit, and we are planning to just send Phantom and RGD. How to say? We want to make a remote audit. So discussing the program and discussing with how to say medical physicists in that hospital.
Okay.
So, yes. So 3D IGRT audit now is a feasibility study. So we have some program, especially so response of the RGD to low energy X-ray, low energy X-ray. Yes.
Energy depends. So if there are no more questions, so maybe let's thank Professor Fukuda again for the wonderful talk. And because of Professor, we have the privilege of delving into this fantastic world of the radiation oncology. And through the radiation oncology project, I think FNCA aims to enhance like cooperation and knowledge exchange among the Asian countries. So is there any other issue? Maybe Dr. Jin? If there's no other issue, let's call an end to today's webinar. And thank you, Professor, again. And thank you for all the audience to attend this webinar. So maybe see you guys, see all of you next time in the next webinar.
Thank you very much.
Okay. Okay. Thank you, Professor.
Thank you.
Thank you all. Okay. Bye-bye.